Flying a drone autonomously through a dense, unpredictable, three-dimensional physical environment is one of the most severe engineering challenges in modern robotics. Surviving that environment requires macro navigation. This is the strategic backbone of autonomy, calculating the optimal, most energy-efficient route across a static map before the rotors ever spin. For decades, the benchmark for this global path planning has been the A-star algorithm. A-star is a graph-based search algorithm that finds the shortest path by exploring a grid step by step until it reaches its target. This animated diagram shows an A-star search expanding across a grid. It operates on a strict heuristic equation, f of n equals g of n plus h of n. It evaluates every node by adding the exact cost from the starting point, g of n, to the estimated cost to the target, h of n. A-star guarantees the absolute shortest route mathematically. However, this deterministic reliability creates a significant computational bottleneck for modern robotics. The algorithm's core constraint is memory. To guarantee the shortest route, A-star must store every single explored node in the system's active memory buffer. Navigating a simple two-dimensional warehouse floor requires minimal processing. Mapping a flight path through three-dimensional airspace requires an exponential volume of data. This grid visualizes the math. The addition of the z-axis multiplies the required nodes astronomically. The memory usage spikes, and the onboard edge compute device experiences catastrophic failure. To scale drone operations into massive 3D environments, engineers must move beyond algorithms that require exhaustive node storage. One solution is to deploy stochastic heuristics, including sampling-based methods like rapidly exploring random trees, or RRTs, and bio-inspired models. RRTs are algorithms that quickly search high-dimensional spaces by randomly building a space-filling tree toward unexplored areas. These methods trade absolute mathematical perfection for feasible compute convergence. The first branch of stochastic planners is evolutionary optimizers, specifically genetic algorithms and differential evolution. This diagram shows a genetic algorithm applying Darwinian mechanics over a city. It generates random spline curves. Mathematical functions use usually smooth, continuous lines between coordinates. It selects the best paths, applying mathematical crossover to evolve the optimal route. Differential evolution uses the same framework, mutating paths with aggressive mathematical differences. This is highly effective for continuous mathematical spaces and multi-sensor fusion sweeps. In dense structured environments, this evolutionary logic is highly effective. Drones running GA and DE capture 16% more data during urban LiDAR missions than those flying standard uniform grids. LiDAR is a remote sensing method that uses pulsed lasers to measure distances and generate precise 3D maps. In precision agriculture, applying GA to analyze images and map specific weed-infested zones yields an 88% efficiency increase over uniform crop spraying. The limitation is time. Generating and mutating thousands of distinct paths demands significant computational power, which is simply too slow for rapidly changing environments. Evolutionary optimizers provide the solution when missions demand maximum structured data yield over raw computational speed. When line of sight is fractured and environments become unpredictable, engineers pivot to the second branch of stochastic planners, swarm navigators, starting with ant colony optimization. ACO mathematically simulates the foraging behavior of ants. Simulated flight paths that reach the target faster accumulate denser mathematical pheromones, which attract the rest of the swarm to the shorter route. This visualization shows the ACO equation in action, balancing accumulated pheromones, tau, against a path's desirability. This targeted convergence is useful for dense forestry. By actively ignoring upper canopy data, the algorithm bypasses occlusions to map sparse ground points below. The trade-off is processing demand. Managing these complex pheromone matrices across thousands of nodes drains processing power, which can lead to lag in real-time adaptation. ACO provides a mathematical framework for navigating predefined occlusions and semi-permeable topographies. Particle swarm optimization approaches the environment entirely differently. It operates like a decentralized, fluid flock of birds navigating vast open spaces. Individual particles, representing potential flight vectors, dynamically adjust their trajectories. They calculate their next move based on their personal best past performance and the entire swarm's current best-known position simultaneously. This specific logic is widely used for marine environments and disconnected swarm missions over oceans. It boasts rapid convergence and high efficiency, allowing for highly reliable task allocation even when network connectivity drops out completely. But that speed introduces a known mathematical constraint, the local optima trap. This 3D landscape illustrates the constraint. Because the flock converges on the current best leader, the swarm can get trapped in a shallow valley, a good path, while missing the absolute global optimum right next to it. To counter this, engineers deploy hybrid PSO variants that inject randomness into the flock, forcing particles to break out of these local traps. PSO trades the guarantee of absolute global perfection for rapid, resilient execution in vast, unpredictable environments. There is no universal path planner in robotics. Algorithm deployment is dictated by the topology of the environment itself. This matrix summarizes the optimal deployments. Urban LiDAR benefits from GA and DE. Dense forestry utilizes ACO. Vast marine operations rely on PSO. A global optimized plan is a static blueprint. The physical world is dynamic. Unmapped obstacles will inevitably intersect the drone's pre-calculated route. To survive the execution of the macro route, the drone must utilize a secondary reflex layer, micronavigation. Micronavigation is the millisecond-level visual reflex system designed purely for immediate obstacle avoidance. The first component of this micronavigation triad is YOLO V8, which acts as the drone's conceptual eyes. YOLO stands for You Only Look Once, and it is a real-time object detection algorithm that draws bounding boxes around specific items in a video feed. This drone camera view shows YOLO in action as it locks onto a target. However, classifying objects requires significant onboard compute power, and high-speed motion can cause blur that disrupts the algorithm. When camera feeds fail, the drone relies on its second component, the Kalman filter, a mathematical predictor. It uses current trajectory and speed to predict where the target will go, allowing tracking even if it passes out of sight. However, because it relies on mathematical models, erratic or completely random zigzag movements can break its prediction accuracy. If the target is lost and collision is imminent, the final failsafe engages, optical flow, the drone's physical reflexes. It ignores object classification entirely, watching only how pixels move. Detecting a rapid outward expansion of pixels, it instantly triggers an aggressive swerve. True UAV autonomy is an inseparable dual-layer architecture. It relies on stochastic macro heuristics to strategically conquer the global map and deterministic micro reflexes to survive.